With the advancement in technology, robots are deployed to solve tasks in outdoor scenarios such as agriculture, mining, and rescue missions. These environments require the robot to negotiate obstacles and navigate through uneven terrain. Legged robots have proven to be the solution that can adapt to such conditions. In recent years, many studies focused on developing controllers for legged locomotion, as it is the most fundamental skill for a robot to solve any task. One of the methods is using behavioral-based control systems. It contains a collection of controllers and a higher-level controller. Each controller in the collection is responsible for one behavior, while the higher-level controller controls the robot by selecting controllers from the collection. In legged locomotion, the collection usually contains walking controllers that allow the robots to move in different directions. The higher level controller is a path planning algorithm that drives the robot towards a goal. In this example, the hexapod has to walk around the wall to reach the goal. In each iteration, the path planning algorithm chooses the most suitable walking controller that brings the hexapod closer to the goal. However, most studies focused on developing legged locomotion on flat terrains. The robot gets stuck when it is placed in an environment covered with small obstacles. Remember, the motivation to develop legged robots is because they can work in outdoor scenarios. Legged robots lose their purpose if they can only work on flat lands because it is more convenient to use a car instead. The proposed solution has the following architecture. Similar to most studies, it uses a path planning algorithm at the highest level. The path planning algorithm controls the robot by selecting the appropriate walking controller. Additionally, there is an adaptation layer that allows the robot to adjust its swing heights for each leg, such that the robot can overcome obstacles in the environment. A leg controller controls the movement of one leg. The idea is to create a collection of leg controllers for each leg, such that a leg can perform a variety of actions. In general, these actions can be classified into two groups. A swing action lifts the leg off the ground and moves it forward to a new position in a swing motion. A stance action keeps the leg in contact with the ground while traversing back to the starting position, pushing the robot forward. The collection of leg controllers is generated using the novelty search algorithm. By choosing different leg controllers, a leg can start and end at different positions and can also have different swing heights. Here are some of the leg controllers from the collection. The first row shows the leg controllers with different starting positions. The second row shows the leg controllers with different final positions. The last row shows the leg controllers with different swing heights. A positive swing height is a swing action, while a negative swing height corresponds to a stance action. Later in the adaptation layer, the robot can adjust its swing heights to control how much it lifts the leg off the ground. A walking controller is composed of leg controllers. The walking controller selects a swing and a stance action for each leg to synthesize a complete leg cycle. Repeating this procedure for all the legs will get 6 different leg cycles that determines the walking gait of the robot. Each walking gait results in a different trajectory. For example, some may allow the robot to travel forward in a straight line motion. Others may allow the robot to rotate on the spot. Most walking gaits move the robot in a circular trajectory with different curvatures. The quality diversity algorithm is used to find the most efficient controller traveling in each direction. The adaptation layer adjusts the swing height of each leg such that the robot can overcome the obstacles in the uneven terrain. The robot has to select a swing height that is just enough to step over the obstacle. Of course, a simple solution is to use the maximum swing height at all times. However, this approach is highly inefficient because the robot is wasting energy to lift its leg high off the ground. Instead, we want the robot to use the minimum swing height when possible and only increase the swing height when necessary. The solution uses Bayesian Optimization to find the best swing height that minimizes energy consumption and collision rates with the obstacles. Here is the final result using the proposed solution. Same as before, the robot has to walk around the wall to reach the goal. To do so, it has to travel through an uneven terrain, which is covered with small obstacles of different heights. With the additional adaptation layer, the robot is no longer stuck when it reaches the uneven terrain, but learns to increase its swing heights to step over the obstacles. When the robot comes out of the uneven terrain, it instantly switches to a lower swing height, hence minimizing energy consumption. Although there are still many avenues for improvement, this study is a step towards developing fully working Lego robots. It provides one solution to how Lego robots can walk on uneven terrains and fulfill the purpose they were originally designed for.